Okay, thank you. Let me first thank all the organizers for inviting me to be here. I'm pretty happy. I mean, maybe this seminar was not shaped for 20 minutes, but I will try to convey the message. And I'm really happy to be here because somehow this topic popped out in my mind in TGSI 17, and it was put on a poster as an idea, and then with some work now was developed and led to some interesting results. So it's a mix of things, and for this reason I'll try to convey the message and without giving too much details, but okay. So the topic is multi-symplectically grouped thermodynamics for covariant field theories, so a lot of things already. And the idea is the following. I mean, I come from general relativity, quantum gravity, and one of the most open problems we have is basically this issue of time in general relativity. So, and the issue of time, so in a context which is completely, fully reparameterization invariant, so fully space-time covariant, is so where there is no notion of time, no notion of and the vanish, and systems are described by vanished Hamiltonian. How can we do statistical mechanics for it? How can we do statistical mechanics so without time? And that's question, which is a big question. It's a very complicated question. Led me to look at the literature by Souriau, which was first trying to provide a notion of equilibrium in terms of fully covariant notion of equilibrium by using a symplectic approach. So this, in fact, was in my study mixed with a more fundamental approach, which is based on information theory, actually, which is the approach by Jaynes, which says that somehow equilibrium is something which is statistical equilibrium is a subjective notion which can be defined independently from any physical characterization of what energy, so Hamiltonian or time, is, in terms of a principle of maximal entropy. And basically, I give you a statistical state here. I'm already in a symplectic setting. So this m omega is imagine your sample space as being a symplectic manifold. I give you a statistical state, which is nothing but a probability density, positive definite, everything. I define a statistical state in terms of a Borel subset of some manifold, of such a manifold with the usual properties, and I define an entropy. I ask for some constraint to be fulfilled, the integral of this distribution to be 1, and some average quantity O, which will be in the algebra of this system that I'm considering. So it will be an observable, the one I choose personally to describe my world, to be constant. And clearly, by a simple variational problem, the stationary statistical state that I get is the Gibbs state. So eventually what I get is a Gibbs state which has the expected value of the observable that I'm interested in, in statistics we would call it sufficient statistics, and the temperature, which is now a Lagrange parameter, Lagrange multiplier, as a coefficient, and clearly, I mean, this can be generalized into the vector, in the case where this E is a vector and B is a vector. So now where Souriau, I mean, enters into the game is that it gives a geometrical characterization of this. Geometric characterization which says that, okay, we don't want to look at any possible observable, but we want to let the symmetry of the system tell us what is the main observable that we want to look at. And from this follows a lot of information. So imagine now we are in a standard setting of a one-dimensional system, so Lagrangian dynamical system. You take a configuration manifold, define a Lagrangian on its cotangent bundle, and Hamiltonian in the cotangent bundle. In particular, restrict to the manifold of motion, which is the quotient manifold, so where solution lives. And there, for example, in this example that everybody knows, which can be a general one, you can define an energy. So this energy will play the role of the sufficient statistic in the Gibbs state. But this energy, what it is nothing but the momentum map associated to the action of the translation along time on the cotangent bundle. So you see that this potential, which is the energy, is encoded in a very specific and more general object, which is a momentum map. In this case, the symmetry is trivial; it's just translation in time. But what if the symmetry becomes more rich? So Galilean, Poincaré. In that case, you would have like a vector value generalization of this notion of energy, which is now not encoding just as a momentum map does, not just encoding the energy of the system, but all the conserved charges that characterize the system. So this is a generalized notion of Gibbs states, which in particular is covariant because it's developed into within the space of motion, so within a covariant space of solution, not anymore at the level of the configuration space of the system. Okay, so given this framework, this nice generalization of Gibbs state, which passed from a very epistemic approach to information theory to a more symplectic characterization of what energy is in a generalized sense, the question was, okay, but what if we look at systems which are fully reparametrized, like for instance GR or the relativistic particle as a simplest example. In this case, we don't even have an Hamiltonian, so the Hamiltonian is 0 by definition, so the system is fully constrained. Can we still, but this object, which is somehow a conserved charge associated to diffeomorphism to the system, can it still play the role of a potential for Gibbs? Can we still define a Gibbs state which encodes somehow covariance with respect to diffeomorphism as a potential? So that was the question. And can we think of this state somehow as being the most general thing from which maybe we can get out some information about fully covariant statistical equilibrium in GR? So the first thing was, can we do that? Can we construct it? Of course, we needed to pass from a symplectic description to a multisymplectic description, because now we're dealing with fields. Yep. So there was a lot of study for that. Was not familiar to me, and I'm only citing here a few of the incredible rich literature which we went through, and it's also beautiful literature. Jim is the famous Gotthard, Eisenberg, Marsden, Montgomery series of paper on multisymplectic geometry, and first for field theory. So where they state and they prove to some extent how the momentum map, the covariant momentum map which they define, really encodes all the information about field theory. So encodes the information about so the constraints of the dynamics, the evolution basically on the Cauchy surfaces of the dynamical fields, but also the stress energy momentum. Everything is contained there and somehow has to be unpackaged. So let me go through this basic setting just to make you acquainted with a multisymplectic formula. So the configuration bundle, which was a set of points in the standard, now becomes a set of fields, which are sectioned over some fiber bundle. Okay, so given some x-oriented and n+1 dimensional manifold, we consider the finite dimensional fiber bundle y over x, it's projection, and in this case this is also a very nice thing. You can think of a field theory as a finite, even if a field is induced naturally an infinite dimensional description. Actually, when you consider finite number of fields, then you end up having a configuration bundle which is finite dimensional. So that's very interesting. So physical fields correspond to section, as I was saying, of this bundle, and you can construct coordinates over fibers. The first jet bundle of the fields, which correspond to this. So basically, let me say. The set of tangent maps basically associated to to this bundle, it plays the role of the tangent bundle of classical mechanics. So those are derivatives of the fields, basically. So now in a tangent bundle, in this setting, we would have points, fields attached to these points, so sections, and derivatives of these with the respective coordinates. Okay, you can define a Lagrangian over this. So these were points, coordinates related to on the fiber associated to the section, and derivatives. You can define a Lagrangian, and we can define an Hamiltonian setting via Legendre transform. Okay. In particular,
how is the Lagrangian defined again?
Yeah, this is a generic way to write it. So this is Lagrangian density. It's a function of a point and the coordinates associated to the fields. So A goes from 0 to n, so 1 to n is the index of the field. N was the dimension, of the fiber. And these are the coordinates x mu, y a. Okay.
So you don't have a definite form. Okay.
No, I'm just introducing it for the sake of the set. Yeah, and So and the same is here. Yeah. The important point is that actually this what will play the role of a cotangent bundle, which is the multiphase space, is defined as a sub-bundle of two horizontal n+1 forms on Y, which elements can be written uniquely in terms of the P, which plays the role of the P0, basically, and P mu A. So these two particular, so you have in the multisymplectic case, you have a lot of momenta coming out. And if this is a specific restriction, which is the closest, if you want, to the standard cotangent bundle description, where you select just a subset of momenta. This subset of momenta are the one, if you want, which are conjugate to the standard variable, so the space and time variable. Okay. So we restrict to this specific setting, which is still very broad and very general, and we can define a symplectic structure. So Poincare 1 form and canonical n+2 form. So you see that now with respect to the 2 form we have a bunch of n, so an extra n labeling, which will play an important role in the following. Okay, so a covariant momentum map can be defined in this case, was defined by, at the same time by different, as far as I know, because I'm by Gotay et al. And also Karinena Ebort and al. Other people from Spain. There is a big school also in Spain. And this can be still defined in this setting. This is now would be before it was a map from from the cotangent bundle to the dual of the algebra. With respect to the action of the group, we defined the momentum map. Here we have something which carries this space of forms. Okay. And okay, so this is nice. We can do that. We have a natural pairing, which is induced topological dual pairing, and a comomentum map, which will be now given by the pairing between the momentum map and the vector, the representation of the. So in this case, is the vector in the algebra of the group we are choosing. So this is very general. So in particular, yes, I just need to check the time. So okay, so in particular, what's important here is that we want this momentum map to be covariant now with respect to the action of the diffeomorphism, actually with respect to action of the one-dimensional subgroup of diffeomorphisms. Okay, so we say that as in the symplectic case, the momentum map is covariant if J is equivariant with respect to the coadjoint action of the group. Okay, so everything is basically consistent with the symplectic case. Now, yeah, the point is, so imagine that now this comomentum map, or the momentum map, is the potential that I want to use. So it's the energy, it's the generalization of the energy in the symplectic case, and now to the multisymplectic case. So it's a huge generalization which encodes the property of covariance with respect to diffeomorphism of the theory. Any first-order field theory that you want to deal with constraints. How can we construct? How can we derive like this Jane's approach, this epistemic approach? So with respect to Souriau, there is a comment Here we are not working at the level of the moment of the space of motion. So we are not anymore working in a naturally covariant space. We are working at the level of the configuration bundle. So we want to give me a system of fields, give me this very fundamental diffeomorphism symmetry. I want to build some potential, and I want to construct a statistical state in terms of that, which may be an equilibrium state. Okay, so I want to do that, but now this part of the game is causing some troubles, because basically you cannot define an expectation value of this object by simply integrating over the configuration bundle. Why so? Because and this is actually very deep, in the sense, in a multisymplectic case, the momentum map is naturally, as being an Hamiltonian map, is naturally inducing a relation between the covariant approach with the canonical approach. So what do I mean? I mean that a momentum map, sorry for switching, is defined in a codimension 1 space of forms. So it must be integrated not on the full space, but on slices of these, in order to define a proper function. Okay. So we need to define. So this object cannot be defined. Hence, we cannot naturally engineer basically the maximal entropy principle in this case. What we need to do is to go to a canonical phase space. So we need to introduce a slicing on the base, which induce like what is called so a foliation, basically, of space-time. So imagine now space-time where this field theory lives, which induce a foliation of the bundle. 3 minutes? Okay, well, I'm very late, so it's going to go. So I imagine that I construct consistently this foliation, and now I want to identify, in particular, I want to select compatible slicing, which is a compatible slicing. What is it? Is basically a slicing where the vector associated to the foliation basically is coincident with the vector associated to the one-dimensional group of one-dimensional subgroup of diffeomorphism. So you can basically diffeomorphism are not screwing, messing up with your foliation. But still, it's completely covariant, okay? So, okay, I will skip a few slides, but don't be afraid. So, basically, what's the result of this foliation? The result of this foliation is that now fields which were defined as section of my bundle over the full space are now defined on foliation, so on embeddings of sigma codimension 1 surfaces on this bundle. And in terms of these fields, and also some what are called covariant fields, something which allows this object to be fully covariant. So with respect to the action of the diffeomorphism, we can define now what is called an energy momentum map, which is basically the shade of the energy of the momentum map on this reduced codimension 1 bundle of fields. Okay, so now this object is pulled back with respect to fields which are attached to single slices of my base manifolds. Okay, this object is still a D star equivariant, and in order to make it a D star equivalent, we needed to work on it. We needed to introduce covariant fields. It was a huge work, but it can be done, and at least for us, maybe it was. So you can define. So what's the result of that? Basically, what you find is the comomentum map now defined in terms of these instantaneous fields, which is basically giving you the total Hamiltonian of the theory. Okay, and is it still 3 minutes, or because it's 20, so it should be okay. So in terms of this properly defined instantaneous energy momentum map, I can define now what is a multisymplectic Lie group thermodynamics. So I can define a statistical state where now fields leaves fields and conjugate fields. Here, what is tau is an embedding field. I didn't explain you what, but it makes everything covariant. So I can define a statistical state in the same way I was defining at the beginning. I can define a partition function. I will use this instantaneous and covariant momentum map as my potential, and I can therefore rule a maximal entropy principle and define what is in this multi-symplectic formalism a state which is an equilibrium state. It's an equilibrium state with respect to the action of the diffeomorphism, so it's covariant with respect to the action of the diffeomorphism, and it has it's basically hidden in this total Hamiltonian or super Hamiltonian, basically all the information about the theory. So the generator of the time diffeomorphism, the generator of the space diffeomorphism, and as we know in GR, in any case, I mean, once you gauge fix this object, then you really end up having something which is an energy and generates the dynamics of the fields. So it's a very general object which has a lot of meaning inside and can be defined properly. So I think I managed to miraculously to get up to the conclusion. So the result is basically that we define this object consistently, and yeah, this is a statistical state in this multisymplectic case. It carries on this very rich momentum map. Once so yeah, so that's too much. Yeah, this basically okay. Let me give you just some remarks. So basically or maybe what is more related to that. So this is what we realized. So it's a gauge group thermodynamic framework, because starting from that state, then you can construct, I mean, assuming that this object is bounded from below, which is a big restriction, you can construct all the thermodynamic relations. So you can actually do that. And you can study what is the relation between the standard dynamics, so variational problems, with thermodynamics in this engineered formalism. Okay, so it's a nice object, and which I was expecting to use in different ways in a physical context. So the fact that basically just one among many, since I don't have time, what does it mean to have you know, that the theory is defined by the constraint. So the constraint B0 select a surface on the phase space where the actual physics, where actual dynamics happen. So now imagine that instead of projecting on this surface, what this Gibbs state is telling you is that you're not imposing a projection, so you're not taking a delta of this constraint on the phase space, but you're taking a Gibbs state, which means that you are asking for this constraint to be satisfied only on average, which means that you're actually taking into account orbits dynamics, which is not true dynamics, it's not physical dynamics, but somehow it's close to be there. So this is a very interesting approach to, if you want, to mechanics, which I don't know, maybe have already been considered or maybe has no actual possibility to be developed more, but which tells me that there is a statistical way in which I can think of symplectic reduction, not through projections toward the manifold of motion, which is sharply this one, but with some dressing, some statistical dressing, where you have solution, but nature has also fluctuation around these that we basically don't see unless we go quantum. And yeah, thank you for this.
One question. Have you considered embedding into a Hilbert space?
We didn't yet, but that's natural because we already have a symplectic. Yeah. Actually, the nice thing is that this object is so even if it's constructed into a configurations bundle, so not in the basically it's not part. It's not naturally part of the algebra of the system because it's not a constant of motion. But with respect to the diffeomorphism, it is. So it's something which is it goes down somehow from the configuration space down to the manifold of motion, as Surya was saying. So it's actually it becomes part of the algebra of the. So also for quantization, this is interesting. We will consider that probably. Yeah.
Thank you.
Thanks.